Dr. Von Dray from Oregon State University on this particular presentation, and she will be our speaker.
Okay, do you want me to wait then?
Okay, yeah, a few more minutes. We have, maybe it's
2:45.
2:45. If I need to.
Precisely.
Yeah, that's what I'll call it.
So while we're waiting, I'm going to be talking a little bit about the octonions, and I know that this is a session on the quaternions. Would anybody like a little bit of a introduction to the octonions before I get to that?
Okay, that would be very nice. Thank you very much.
Like, use all the time you've got, you know? Like,
Do you know how to work
okay, so I am assuming that people here will know about the quaternions. So we have 3 square roots of -1, I, N, J, and K. And they all square to -1, and they have a multiplication rule. I times J is K. But they anti-commute, so J times I is minus K. Those are the quaternions. You get an isomorphism with Pauli matrices, which I will explain in the middle of my talk. But if you want to go do bigger than that, you go from the quaternions with 3 square roots of -1 and a real part, so they have 4 parts, that's why they're called the quaternions. The next step up in the Cayley-Dixon process are called the octonions, and there you have 7 square roots of -1 and a real part, so there are 8 parts altogether. The ones you know and love are labeled IJK. So here is the quaternionic multiplication table in here, but now we have 7 more, and we label them L, IL, JL, and KL because we run out of letters. But now any one of these line segments on the diagram you can think of as a circle, matches up, and then that forms a quaternionic subspace of the octonions. So you have IL and K and JL also form a quaternionic set. And in particular, we often use the one straight up the middle. We will relabel everything that you used to think of as the square root of -1. We call it L, and then we will use K, L, and KL as our quaternionic set. I'm just giving an introduction while we're waiting for people to the octonions, while we're waiting for people to come in.
Exactly.
So, are there questions about that? With the quaternions, you lose commutativity. I'm a physicist. That doesn't bother us at all because quantum mechanics is not commutative. When you go to the octonions, you lose associativity. If you try and go bigger than that, then you have 0 divisors. And at that stage, as far as I'm concerned as a physicist, you lose all the algebra that you really want. Okay, there is a microphone. I will try and use it, but I also strongly recommend that you all come up to the front half of the room if you're having trouble hearing.
I tend to agree. Come on down.
So, I will use the microphone to tell you if you're having trouble hearing. Come to the front of the room. I did have a shower this morning, I promise. Okay, I think we're allowed to start now.
Okay.
All right, so when Johannes introduced me, I am a physicist, and so I really thank the mathematics community for welcoming me and listening to some physics kinds of comments. This is work with Tevian and Dray, but we have also over the years worked with quite a number of different people. In terms of the outline, I'm going to tell you a little bit about physics, a little bit about Clifford algebras, but what I really want to do is describe for you how to solve probably the most important physics equation in terms of elementary particles that there is, which is called the Dirac Equation. So I'll assume that most of you don't know anything about the Dirac Equation. I will introduce it, and then I'll show you how to make it quaternionic, and then how to solve it. Then look at Lorentz transformations, which are not just rotations in three-dimensional space, but the boosts from special relativity. And then talk a little bit about some even fancier mathematics, Albert algebras, and solutions in terms of those things. So, physics is about the relationships between physical quantities. So we don't just have equations, but those equations carry physical meaning. And for us in particular, if you're doing special relativity, the most important equation is the one that for a particle relates, or in anything that's moving at relativistic speeds, relates its energy, its three momentum, so this is really px squared plus py squared plus pz squared, and its mass m. So this energy momentum relationship is the one that we really want to see in all relativistic particles. I will write it with an Einstein summation convention, so P's mu runs over the indices for time and three spatial ones. P0 then is the energy, Pi, Pj, P1, P2, P, and 3 are the three spatial ones, and there's an m squared. All right, so is this notation familiar? Okay, so now, here is the Dirac equation. So it's I gamma mu d mu minus m psi equals 0, and the only thing you know in here is probably, here's an I, d mu is a partial derivative with respect to x mu, and m is a scalar. But I need to tell you both what this gamma is and what the m is. Oh, sorry, what the psi is. You know what the m is. What the psi is. But I will comment that this is just simply a first order ordinary differential equation with constant coefficients, so you all know how to solve that. And if you put in the solution that psi changes with space and time, like e to the I px, then these derivatives pull down a minus, or e to the minus I px, pull down a minus I to cancel that, and put a p mu in here, and you end up in the usual way with ordinary differential equations, getting an algebraic equation that you solve instead of a differential equation that you solve, and I will be doing that throughout. This is called the momentum space version of the Dirac equation, because these are the momenta of the particles. Now, what are the gammas? The gammas are elements that to mathematicians would be called Clifford algebras, and to physicists who can never remember fancy math names, they're called gamma matrices because they're written with gammas. All right? But so here's a gamma, but the Clifford algebras all abstractly solve this anti-commutation relation. So they've got indices, space-time indices, gamma mu with gamma nu anti-commuted means gamma mu times gamma nu plus gamma nu times gamma mu has to be twice the metric of the space that you're looking at. So it's plus or minus 1 or 0. The rank 1 objects, because they have these space-time indices, linear combinations of these rank 1 objects, which are just single gammas, are vectors. Interestingly, the rank 2 objects, if you take products of the Clifford algebra elements, the rank 2 objects become the Lie algebra, the infinitesimal Lorentz transformations in those same dimensions. Okay, so now what I want to do, in fact, is show you some of the notation that we use that's going to be easier to understand when I make things quaternionic, that build this Clifford algebra out of simpler things. So these three matrices here are the Pauli matrices. They're 2 by 2. Over the complexes, here are some complex numbers. They're Hermitian, they square to 1, they anti-commute. If I add to them one with an index 0, which is just the 2 by 2 identity, then I have 4 things. And then I will also sometimes want to put a tilde over one of these things, which is just the trace reversed version. So I subtract, it's the original Pauli matrix minus the trace. Notice that all three of these are traceless, so all I'm really doing is changing the sign on the identity. This 0 index, it corresponds to time, and so this in fact the trace reversal always corresponds to raising or lowering an index in relativity. All right, so now what I want to do though is build a set of gamma matrices for 3+1 dimensions. These are the space-time dimensions in which we live. And if I want to build those, then what I need is 4 different things which anti-commute with each other. The problem is the Paulis, there are only 3 of them that anti-commute with each other. So I'd like to build them just out of Paulis, but I only get 3 of the 4 that I need. So to get a 4th, I take a tensor product with another set of Paulis. And so these 3 things plus this thing build my set of 4 things. All right, so those are my 4 gamma matrices. This isn't explicitly a chiral representation of the Clifford algebra. Chiral means that it's explicitly block off diagonal. So now we see that these gamma matrices are 4x4 matrices over the complexes. Right? So now, if these are 4x4 matrices over the complexes, this is just a set of numbers, these are all numbers, there's a 4x4 identity matrix, then what is psi? Psi then is a 4-component complex column. And now, if I plug in all of the p's and what the gammas are, here's explicitly the 4x4 matrix in terms of block 2x2 matrices. And you see that what happens is that when I have this mass term, if the mass is not 0, what the Dirac equation does explicitly is combines, it mixes up thetas and etas when I do this matrix multiplication. All right, so now I introduced already, if you came a little bit earlier, the octonionic multiplication table. Let me just comment that the quaternionic multiplication is this circle in the middle, I times j times k. The octonions are like super duper big quaternions, and there are 7 square roots of -1, so there's some extra ones in here, I and IL, and L is in the middle. Any one of these straight line segments you can think of hooking up the ends, and then it becomes a circle just like IJK, and it is a quaternionic subspace of the octonions, just like the ones you already know. As soon as I move to the either the quaternions or the octonions, now I have something new I can do with my Pauli matrices. Oh, sorry, wrong side. First of all, I just wanted to comment that the Paulis, if you take I times the Pauli matrices, now I have 2x2 things that are anti-hermitian. They square to -1 and they anti-commute. And so you might, this starts to sound familiar, and indeed, these are just a representation of the quaternions. There is an isomorphism between the quaternions IJK and I times the Paulis. And so I will use that isomorphism in a couple of minutes. All right. I showed you the modern way of writing the Dirac equation, but it's not the way Dirac himself wrote the Dirac equation. Dirac himself multiplied the whole equation through by gamma 0. All that does is mix up where the various m's and sigmas and everything are, but I'm going to use this version of the Dirac equation. Notice now the mass term still mixes up theta and eta the way it did before. But it also now, because it is the thing that's off diagonal, as a 4x4 matrix, it anti-commutes with all the other gammas. And in fact, it's the time-like term with mu equals 0 that is just the identity that doesn't anti-commute with everything else. All right. Now that I've mentioned the quaternions and the octonions, I have this cool thing that I can do with the Pauli matrices, which is I can extend them. This one is all real and this one's real, but this one is pure imaginary. It's got an I in there. So as soon as you're talking about quaternions or octonions, you say, which I? And I will say to you, I don't care. Let's make, instead of just one like this, let me make 3 like this for the Quaternions, or 7 like this for the octonions, right? And so now I have more Pauli matrices. And if when I do that, I go back and I make a bigger Clifford algebra by having more gamma matrices, because now I've got more Pauli matrices like this, I get more things that anti-commute. And what's interesting is these anti-commute both by the structure of the real and imaginary Paulis, but also because those quaternionic or octonionic units within them anti-commute. So this Clifford algebra has the structure that I want it to have because it miraculously uses the anti-commutativity of the quaternionic and octonionic units to give me more things. What this allows me to do now is to go back to my Dirac operator in momentum space, which was like this, and now instead of putting this M on the off diagonal to make it an anti-commute, I actually bury it in with one of the new quaternionic or octonionic units that I had, and now I have something which is block diagonal, and the theta and the eta then don't appear to be coupled, but what happened was this object is now quaternionic instead of just being complex. So I have 2 by 2 quaternionic things instead of 4 by 4 complex things, and in the same way, the column that multiplies it, I put the theta and eta together with some k-like things. I put a sigma k in here. Right, so I've given you, now what I've done is taken a 4 by 4 complex thing and I've collapsed it using the quaternions to make a 2 by 2 quaternionic thing. Right, is all I've done. And if I didn't write it down here, but if you go back to my original construction of the gamma matrices in terms of tensor products, so sigmas with sigmas, it's basically using the isomorphism on that first set of Pauli matrices, the first set of sigmas. I made those be quaternionic, and then this is how I get these 2 by 2 octonionic things. Now, it turns out that, well, I'm just going to define, this is a 2 by 2 matrix. I'm going to call it P tilde, and I'm going to use a capital theta for now this theta minus sigma eta. So the theta is a 2-component column with quaternionic entries, and this is a 2 by 2 Hermitian matrix over the quaternions. And the Dirac equation now has this beautiful simple form like this. It's even simpler than that. You can, because these sigmas now carry the Lorentzian index on them, this is a Lorentz vector. And now some geometry starts turning out. This is a 2 by 2 Hermitian matrix, and it turns out that the Lorentzian norm of this vector is just the determinant of P. And, or I could think of it as the trace of P tilde with P. Remember, P is just trace reversal. So P tilde with P trace is also the Lorentzian norm. And the Lorentzian norm is just, for us physicists, is just the energy-momentum relationship that we want. But now, if I do the quaternionic case of this vector is in 5 plus 1 dimensions. If I choose, so 5 plus 1 dimensions, what's happening is I'm trying to make this m term here look like these other p's. This is px squared, py squared, and pz squared. And now I just notice in this equation that the m squared looks exactly like that. Right? So I'm just making this look like another dimension. And so if I choose this vector to be null in 5 plus 1 space-time dimensions, then it is massive in 3 plus 1 space-time dimensions. These extra momentum-y looking directions are just the mass. But the algebra of those things is just what you want it to be. All right. So here's the Dirac equation. P tilde theta is equal to 0. I want the energy-momentum relationship to be true, so I'm going to pick P so that it's null in 5 plus 1 dimensions, so that it's massive in 3 plus 1 dimensions. And then it turns out that if I choose for any theta that I've got here, if I choose theta to be theta theta dagger, proportional to theta theta dagger, it turns out that I always have a solution. And for those of you who are getting like lost in all the mathematical symbols, I wrote it out nicely for you just in terms of columns. So B and C are just elements of the quaternions. So this theta theta dagger is the outer product of BC with B bar C bar, and it is just this. Right? The statement that it's null is the statement that the determinant of that equals 0. But why is the determinant of that 0? Well, the determinant is multiply these two things together and those two things together and subtract. But that's just the fundamental algebraic relationship on quaternions and octonions. That's the norm relationship, that the norm of B squared times the norm of C squared is equal to the norm of BC bar. Right? So all of this is working because of properties of the inherent quaternions, and in fact I can do an octonionic version of this as well. Now my claim here that to satisfy this equation, if I take this matrix and I trace reverse it, and then I multiply by BC again, notice that it's trivially 0. I get minus the norm of C squared times B, and then BC bar times C. And it's always 0. So it's very simple properties of the quaternions or the octonions that are solving this very important physics equation for us. Now what we really want to know is, we need the Dirac equation to be Lorentz invariant. If I look at a particle from a different reference frame, the laws of physics need to still be the same. So how do I do Lorentz transformations? Remember I said that the Lorentzian norm was just the determinant of P. And so if I do any transformation of that matrix that preserves the norm, then it will be a Lorentz transformation. For quaternions, I just pre and post multiply by m and m dagger for wherever the determinant of m dagger is equal to 1. I'm not writing just that determinant of m is equal to 1 because there are some commutativity issues when you're over the quaternions. Turns out for the octonions, you don't get all the Lorentz transformations by doing this. But you do get all of the Lorentz transformations if you nest. So you do one transformation and then you do some other transformation. Because the octonions are not associative, this doesn't collapse to just a simple pre-post multiplication by one matrix. So you have to use all of the things like this, and then you can even do Lorentz transformations in what turns out to be 9 plus 1 dimensions. By the way, 9 plus 1 dimensions is the dimension of superstring theory. And which is, like, I think not an accident. Okay. So now what we'd like to know is that the Dirac equation, P tilde theta equals 0, is Lorentz invariant. But if we know that P is n times theta theta dagger, then all we're doing is doing a transformation on theta, on all the thetas, right? And then it's sort of manifestly Lorentz invariant, the Dirac equation. So it has the properties that we want. All right, I have 1 minute left. And let me just say that the most beautiful mathematical thing we can do now is take both P and theta and embed them and a scalar omega and embed them in 3 by 3 Hermitian matrices over the quaternions or over the octonions. And when we do this, then when we do a Lorentz transformation, here's the original 2 by 2 Lorentz transformation. When we do this transformation, it does the correct transformation on both P and theta at the same time. And so we're taking both the momentum of the particle and the theta, which is the solution of the Dirac equation. We put them together in a united object, and Lorentz transformations happen nicely on those.
That's okay.
Okay, so I will just comment that I can rewrite this in case you know this language. I will say it. If you don't know this language, just ignore it for one slide. But the Freudenthal product of 2 of these 3 by 3 matrices being 0 encodes both of the equations for the Dirac equation. Its nullity and P tilde theta equals 0. these solutions, then it turns out that solutions that are like that are in OP2 cross R. And it turns out that even if I do a octonionic version here, the solutions turn out to be quaternionic. My conclusion is that mysterious physics, for both physicists and mathematicians, is encoded in awkward mathematical structures over the complex numbers. But when we embed these carefully in well-defined mathematical structures over the quaternions and the octonions, then the solutions have these beautiful mathematical properties and geometric properties. And this makes Tevian and I really feel like the reality of the universe is probably much better described in these ways. Thank you.
Thank you.
Any questions? Any questions? Yes.
Why is the Dirac equation so important?
So the Dirac equation describes, you can't go back. The Dirac equation describes the motion of all of the fundamental particles. So quarks and electrons and neutrinos, everything except the particles that carry forces. So not the photon, not the W's and Z's, but everything else. Yes?
I don't know if I just misheard you, but did you say something like octonions are not associated?
I said octonion. I don't know what I said.
Okay.
But what I meant to say is the quaternions are not commutative,
Okay.
but they are associative. But the octonions are not even associative. And it's interesting because there are many famous physicists who wrote one paper about the octonions and then threw up their hands and quit because they didn't know what to do about the non-associativity. It was like too nasty. But this result about the Lorentz transformations coming from nesting, you actually have to use the non-associativity to rescue all the transformations that you want. And once you know about nesting, the octonions work much better than most physicists think.
So the non-associativity is exploited.
Is it? Yes, exactly. The non-associativity is exploited.
Very interesting.
Yes.
Thank you.
Any more questions? Oh. Do you have a question?
Yes.
Yes, please. Oh, sorry.
Now, analytic model for the sitter space rather than Minkowski space where you have octonionic algebra.
Wouldn't that be nice? Not that I don't know.
Okay.
Okay, thank you. Any more questions? Oh, yes, there's another question.
Yeah.
Is your construction here specific for spin 1/2 particles only?
Yes.
Okay.
The Dirac equation is specific only for spin particles. Yes.
Anyone else have any more questions for Manogue? Oh,
Manogue.
no, Laurel.
So this is kind of joining of the two, the subalgebras of the split octonion we've talked before. Are there any links here in terms of like particular physics-related structures that are connected to those subalgebras that we saw before, Jim?
So we're exploring that question
Next year.
right now. Next year. We don't have anything we're ready to say yet, but yes.
Okay, that sounds great.
That's why Leiter was doing this project, is because we want to know more about the split case.
Okay, and any more questions for? I am looking.
Corinne.
I am looking for Corinne, yes, okay. I am looking, okay. Well, thank you very much. This is wonderful.
David's coming up to see what it was.
David, do you want to run on my machine or do you want to run?
Sure. Is it a PC?
Yeah.
That'd be great, thank you.
Yeah, hi, how are you? Yeah, I remember, as a matter of fact, I followed you up on something you told us, now remember you were talking about Hamilton's notion on Rodriguez, the geometry, and I decided to follow it up, and I looked at Hamilton's figure, 15 out of that, and I actually helped put together a report.
Yes, I do.
Inspired that to go further with that, because you were saying something about it.
I believe that they're digitizing.
Yeah, we
And
may-
then it's gonna be on the, I mean,
We'll put it on the site.
And because it's so
Okay, so
precise.
they'll be accessible.
the whole talk is.
Okay, all right, okay.
It was a basic, yeah, right, because the Hamilton, you'll see tomorrow. Yeah, right, and I actually worked out the calculations, I sat there.